that. That's all that's going to be on it. So I brought up OneNote. We can go to any homework, any example, exam, anything else that you want to go to. So we can just make a list really quick and try to cover as much as we can in the next hour and a half.
Can we talk about defining shear and moment in terms of a variable a little bit more?
Yeah, so shear and moment in terms of like a distance x.
Right.
Yeah, and that's a fundamental part of shear and bending moment diagrams. Yeah, Pat.
Just kind of going over where to take section cuts with
Yeah.
the loads that are on.
Yeah, so where to make your cross-section cuts. And some of the feedback I got from one of the graders today had to do with actually plotting out shear and moment diagrams. And so we'll kind of talk about that as well too, because the functions that you get for a beam, you might have like 3 different functions. And so when you're plotting out your results, you got to remember that each function has a set domain. You can only use that one function between 2 specific points on your beam. If you plug in a value outside of the domain, it wouldn't have any bearing in reality. And so we'll talk about that a little bit as well too, like what the domains of each of those functions are going to be. Yeah.
That's sort of table form for finding moments of inertia?
Absolutely. So the table for finding the centroid, like x bar, y bar, ix, iy, whether it's about an arbitrary axis or maybe the centroidal axis, we'll go over that table. I'll try to use up as much space as possible this time. We'll do a big comprehensive diagram as well too. What else do we want to talk about? Well, that's enough to start with. We can talk about this for an hour at least, probably a week if we really wanted to. But if more specific questions come up after we start going through this, let me know. Again, specific questions about homework problems or the example final that's been posted, any questions about that, fair game as well too. So let's start talking about shear and moment functions and diagrams as well too. So these first 2 points are really related to each other. So the question is, if I have some beam with some arbitrary loading, number 1, where do I make my section cuts? And then number 2, how do I calculate V and M as a function of some variable distance? So let's make up a beam here. And so I'm going to try to make this as thick as possible. So I'm recording this in 1080. I tried recording it in 4K so you could really zoom in, but after like 45 minutes, my camera starts to get a little bit hot. It's actually not supposed to go past 20 minutes, but so 1080 hopefully is going to be enough resolution for you to be able to zoom in on this after the fact. When I upload it to YouTube, it takes about an hour for it to transcode it in the higher quality, so just keep that in mind. If you go to YouTube and it's really fuzzy, it'll take a little bit of time for YouTube in the background to update it to full 1080p. Same thing if you're looking at it on a smartphone, you might want to go to a computer instead. Okay, so let's do a beam. I've got a pin on the far left end. I've got a roller somewhere to the right, but we still have this overhanging section right here. So we would call this an overhanging beam. And we need to add some loads as well too. So we're not going to put pure values on these, but let's put a linearly distributed load, a uniformly distributed load between the pin support and some arbitrary point in between the supports. Let's go ahead and put a point load out here, and why not maybe right here. Let's go ahead and put a couple moment as well too. So those are kind of the 3 main types of loads that we've looked at. This type of uniformly distributed load is relatively easy to deal with because you're just dealing with a rectangular shape. But 3 different types of loads, that could be fair game for the exam. How many section cuts is this going to require? 3. So that's maybe a little bit much for the exam. I mean, probably 2 is going to be fair game for the exam, but some combination of multiple types of loads, maybe a couple different section cuts. And let's talk about why we need to make 3 different section cuts. So let's continue making this a bit of a more of a complete free body diagram. So here, I'm just going to define a coordinate system, the traditional one that we use, and I'll put some at least variable names on these loadings. So my uniformly distributed load, I'm going to call it W. It has a height of W. We're going to say that this couple moment right here, I'm going to call this M sub B. And then this, we're just going to call this, we'll just call it P1. And so I'm missing a little bit of geometry as well too. And we'll label these points point A, point B, point C, and point D. So I need some geometry associated with these as well. And so I'm just going to call this LAB. We'll call this LBC, and we'll call this LCD. Okay, so we've got all the pieces of a common problem that we might have to deal with. Here, everything's left in variable format. Usually for homework problems, I'll give you numerical values for each of them, but keep in mind, we've had some homework problems where things are variable as well too. So you need to be comfortable whether or not you have discrete values for these or whether you're dealing with variables. So we'll go through this as much as we can, just leaving everything in variable format. What else am I missing from this to make this a complete FBD? Exactly right. So here I've got a pin at A. So I've got two unknowns, and usually we represent that by an unknown vertical force and unknown horizontal force. So I'm going to draw that here. We'll call the vertical force A sub y, and we'll call the horizontal force A sub x. At the roller, all that a roller does is resist vertical displacement, and as such, the only unknown that I get is just a vertical force, and I'll call that Cy. Okay, so earlier in the term, we looked at a beam like this, and we were able to calculate all of those support reactions, and that's usually going to be your first step in a problem like this as well too. Even if you might not necessarily need all of the support reactions to calculate the internal shear and moment across the length of the beam, I'll often ask you for that. So I mean that first step, finding the support reactions, even though technically we learned it maybe 5 weeks ago, it's still applicable. It's still something you have to do for the final exam as well too. So we'll just go ahead and say step number 1 would be to find all of these support reactions. So how do you go about doing that? How do you go about solving for these unknown support reactions, AX, AY, and CY?
Take a moment, to solve the moment around A or C.
Yeah, so if I sum the moments about A, oops, let me make this a little bit thicker. If I sum the moments about A, why does summing the moments about A help me solve for one of those reactions quickly? How many unknowns end up in that equation?
One.
Yeah, just one. I mean, we're assuming that we have P1, M sub B, W. We're assuming we have all of those, all the geometry. The only unknowns that we're talking about are the support reactions. So here, if I sum the moments about AY, the line of action goes right through point A, so it can't cause a moment about it. AX goes right through point A, can't cause a moment about it. CY, however, does have some perpendicular distance from point A, and so CY is going to cause a moment about it. What about W? Is that going to cause a moment about A? Absolutely. And so at this point, what do I usually do with that distributed load to make it so I can calculate the effect of its how much moment it has about point A? Yeah, we usually, I don't know if I would want to say convert it, but let's say we represent it as the resultant of this load, because this is going to get tricky, and I've seen a lot of students cut up making this mistake. They'll just erase all of W, and they'll replace it wholesale with the resultant force. And then when we get to the next step, they'll forget that it's actually a distributed load. And then that messes up the shear and the moment equations, and we'll talk about why in a second. So I strongly recommend leave the distributed load on there, but then draw a resultant force, and oftentimes we denote that with kind of this italicized O or 0. on the actual line of the arrow itself. And that's just a visual cue, at least it is for me, that this is not replacing this. This is just kind of summarizing the effect of this distributed load. So the distributed load is still there. We're just kind of summarizing its effect. And so as a result, in this case, what is the magnitude of that resultant for that uniformly distributed load with a height of W and a length of LAB? It's just the area underneath that diagram. And we have the entire loading diagram here. Our global free body diagram encompasses this entire distributed load. And so it's the area underneath that distributed load, which is just a rectangle, height W, width LAB. So W times LAB, exactly right. And what else am I missing in terms of representing that resultant? Yeah, the actual location of it. And so because it's a rectangle, well, I mean, for any shape, for any resultant, the location of the resultant force application is at the centroid of the distributed load. Thinking of this distributed load as just a shape. Here's a rectangle, so the centroid is really easy. It's just half the width. So I could represent the width from here to here as L AB divided by 2. It would be the same thing going to the right of the resultant as well. Okay, so now we've got a global free body diagram that we can really deal with in terms of summing moments, summing forces, because I've changed everything down to kind of the simplest form that we could then use. So we won't go through all of the equations here, but like Dilshad said, we've got summing the moments about A is going to allow us to solve for Cy because this distributed load causes a moment about A. Based off my coordinate system up here, I'm saying that counterclockwise is positive. So is this causing a positive or a negative moment about point A? Yeah, negative. It's causing a clockwise rotation about A. And as such, we need to put it up here as a negative value. So minus, and the force is W times L AB. And what's the moment arm? Divided by 2, yeah, because the line of action of this resultant is going right down here, and the perpendicular distance from that line of action to this point A is just that LAB over 2 that we calculated earlier. So LAB divided by 2. All right, what else causes a moment about point A? Let's just kind of go from left to right and deal with things that way. Yeah, so Cy does, but going from left to right, what causes a moment about A first? Yeah, this couple moment here, M sub B, right? Because it shows up on my free body diagram, it's basically going to be part of any moment summation equation that I can write if it shows up on my free body diagram. So that means this M sub B causes a moment about A. Is that going to be positive or negative? Yeah, it's negative. It's going clockwise as well too. Our coordinate system says that positive is counterclockwise, so this will show up as negative. So is that negative M sub B times LAB? No, why not? Yeah, it's already a moment. The units wouldn't work out if I was multiplying it times a distance. I'd have force times distance times distance. I'd have force times distance squared. That's not going to work out, right? So a moment, a couple moment, again, and we talked about what might cause something like this. In other words, we talked about something that might cause a moment without causing any net force at that location. It's like I stuck in a screwdriver and I just twisted the screwdriver, right? With the screwdriver on one side, my hand is pushing up maybe 5 pounds. On the other side of the screwdriver handle, my hand is pushing down with 5 pounds. They cancel each other out in terms of forces vertically, but together they're both causing a torque about that screwdriver. So it's like I shoved in a screwdriver and I'm twisting it. No net force effect, but it does apply a couple moment to the system. Yeah.
So it seems to me like the axis for that moment is coming out of the page.
Exactly right. The axis of the moment is coming out.
Axis isn't, A is not on that axis. So I always had trouble understanding how that would cause a moment at A and not a force at A.
Oh, sure. Yeah, great question. So when you're summing the moments about, yeah, that's a good question. When you're summing the moments about an axis, right? Our definition of a moment is a force times a distance. So let's just think about it this way. So let's just go back to kind of 2D like we're doing right here. And let's say that I've got a couple moment applied right here. We'll just call this M sub couple. And we're interested in the moments about this point. I'll just call it point A. And so exactly right. The axis that we're actually interested in is coming in and out of the page at us. But let's just think about it this way. This couple moment could be, a way that we could cause this couple moment would be like a wheel or a screwdriver in there, twisting it around with like a little bit of force down, a little bit of force up. So I'm just going to redraw this in terms of like an equivalent system, like what would cause this. So I'm going to put a little handle right here, and I'm going to put, let's just say, some force up and the same amount of force going downwards, right? This force with some small distance, some perpendicular distance in between it, this force couple is exactly equivalent to this moment couple, right? This force couple is only causing a couple moment. So these two types of loadings are equivalent. And as such, if I'm trying to figure out the moment about point A, just looking at the force couple itself, I would look at the perpendicular distance here and the perpendicular distance here. And so here, let's just go ahead and call this distance L. And so then what would this distance down here be? L plus that distance D. So now if I sum the moments about point A, it's going to be equal to what? Let's do the same counterclockwise as positive. Does this first force couple cause a moment about A? Yeah, how much and what sign?
Positive.
Yeah, positive because it's counterclockwise, and the magnitude Fc times L. So Fc times L. Does this couple moment cause, does that force couple cause a moment about A? Yeah, is it positive or negative? And what's the magnitude? Fc times L plus D. So what you're going to see is this Fc times L is going to cancel out with the first Fc times L over there, and all that we're left with is just negative Fc times D. And the way that I would calculate this couple moment is Fc times D, right? So that's why, that's another way of looking at it. It's just we don't really care about what these forces are or what the distance is between them. We just care about the moment effect, and that's really all that couple force is causing. Does that help? Okay, great. Probably should have went over that 6 weeks ago, right? It's always tough to know what's causing the conceptual kind of issues. But that's a really good question, so hopefully that'll help clear some stuff up. Okay, so getting back to what we're talking about here, we just incorporated the effect of this couple moment at B into our moment equilibrium equation about point A. And so let's just keep on going from left to right and figuring out what else is going to cause a moment about A. And somebody mentioned it earlier, CY has some perpendicular distance from its line of action, which is vertical, all the way to point A. And that's going to be causing a counterclockwise rotation about point A. So that's going to be a positive value in our equilibrium equation. And that'll be plus CY. And what's its moment arm? Yeah, both of these lengths here, LAB plus LBC. And then finally, we've got this single point force P1. Its moment arm from point A is the entire length, so LAB plus LBC plus LCD. And it's going clockwise about point A. So I'll finally get a minus P1 times LAB plus LBC plus LCD. So that should be review as far as populating that equation. It's really just finding a free body diagram running equilibrium to solve for the unknowns that you don't know about. And that's the crux of what we're doing when we make a section cut as well too. So all of this kind of week 4, 5, 6 stuff is really all that we're doing when we start making section cuts. So you want to make sure you're really comfortable with this, because we will add a little bit of a wrinkle later on when we're dealing with, instead of this being LAB plus LBC, it might be X or something plus X. And so that's why you need to get really well versed in this before we start getting into the variables. So we're not going to go through the rest of the equilibrium equations here, but this is how we would solve for Cy, because Cy is our only unknown. That's why a problem like this is not that great to deal with in terms of variables, because you would end up with Cy is equal to some 3 terms divided by some multiple terms of length added together. It gets to be a little bit uglier. So this is nice to have discrete values for. That's why I'm not going to go through and solve for what Cy is equal to. But basically, you would just use algebra, move all these other terms to another side, divide by LAB plus LBC. That's how you would get Cy. And then finally, just for review purposes, if I wanted to solve for AX, I would just sum the forces in the x direction equal to 0. That's going to tell me that AX is equal to 0. And then once I already have Cy, it doesn't really matter whether or not I have AX. I have 2 different options to solve for AY. What could I do? You get some of the forces in the y, because once I know Cy, I know all of the forces going vertically except for AY, so it'd be the only unknown. Or I could sum the moments about point C, and I could have done that to start out as well too. So a couple different options. To find AY, I could either sum the forces in the y direction equal to 0, or I could sum the moments about point C equal to 0. Either way, that will give me AY. So still fair game to do support reactions on the final exam. That's part and parcel to what you're going to be doing for the next steps. And so now let's figure out what the next steps are. So we've got all of our unknown support reactions calculated. But our real query is trying to figure out, well, what is the internal shear force and the internal bending moment that this beam has to carry at any given cross section? So what we've done before is I've told you, well, here's some arbitrary point E. I might give you the location. I say, make a section cut there and tell me what the internal shear force and bending moment is. Now, that's just kind of the first step before we get into the way of representing all the possible internal shear force and bending moments at any given location across the beam. And again, the reason that we care about that is sometimes we might have maybe a splice or something here where we care about the specific shear and moment right there, so I can design that splice. But more often than not, we want to figure out, well, where's the location of like the maximum moment? Or where does the maximum shear occur? And so defining these in terms of a variable distance allows us to kind of plot out and figure out where does the max moment happen, where does the max shear happen. And then eventually that'll also allow us to do things like find the deflection of the beam, figure out whether or not the beam's going to fail. That's all kind of EAS 212 material. So you will be doing this again. I was just talking to the CE 324 instructor yesterday, and he's going through shear and bending moment diagrams as well too. The difference being that his are a little bit trickier. He's got 2-dimensional frames and things like that, where instead of a beam, maybe he's got a frame that looks something like this, where it's got 90-degree bends, or maybe a 45-degree bend over here, and you've got to do a shear and bending moment diagram for each of the elements. But so it's getting a little bit more complex, but really fundamentally, it's still just the same kind of work. So I'm going to go ahead and erase what we did for the support reactions, and now we're going to talk about how to actually plot out, we'll define the functions and then plot out the internal shear and bending moment as a function of location. And so this is where we start getting to kind of this second question right here, is where do we actually make our section cuts? And so we'll just go ahead and call this step number 2. And here we're going to say define our cross-section cuts and create the free body diagrams that we need. So the rule about how many section cuts you need is that you need enough to fully define what's going on internally across the length of the beam. Another way of thinking about that is I need to make section cuts that are applicable to a specific domain. I need all of them to make all the domains added up the full length of the beam. So the point is, let's just go ahead and make a first section cut and just kind of see what happens. So here, I'm going to make a section cut, just some arbitrary point in between A and B. And I'm going to define the length, the distance from A to that section cut, I'm going to call that x1. The subscript 1 is just telling me this is my first section cut. We might need more. We'll find out in a second. But for your exam, I'm going to have you measure x from the same location on the beam, regardless of whether it's a section cut over here or anywhere else. You're always going to be measuring from the same location. So that the 1, the 2, the 3 just means different section cuts. And what I'm going to do is I'm going to choose either side of that section cut to keep for my free body diagram. The other side I'm going to replace with an equivalent shear and moment that keeps everything in equilibrium. So which side do you want to keep here? Probably want to keep everything to the left, right? Number one is that this distance x is a lot easier to deal with than like this entire distance right here. And what is the distance from this section cut all the way to this end? It's the entire length minus x. So it gets really ugly really quick. It would be LAB plus LBC plus LCD minus x. And you don't want to deal with that, especially when you're summing moments, right? So I think here it's going to be easier to keep everything to the left. So let's look at our first section cut, and let's start making a free body diagram of it. So I'm going to make this a little bit bigger. I've got some portion of the beam, and now I've got my section cut right here. And we said this distance is going to be x1. That's a very incomplete free body diagram, so help me finish it. What else do we need to put there? Yeah, the actual, so all the loading, whether it's reactions or external loading, AY is a support reaction that's definitely going to go there, right? And we've already calculated AY from the previous subpart of our problem. Again, we didn't actually do it here, but you would have gotten to that point previously on this problem. AX I'm not going to show because AX is just equal to 0. That's not going to be a problem. Okay, what else? Yeah, but I don't know. I mean, I'm to the left of this resultant, so I'm not going to put it up there. No, that's right. I have to, because this is a common mistake. If you replace this entire distributed load on your free body diagram originally, you might make that mistake and say, all that I have here is just that point load R, which is not the case. This point load R is a representation of the effect of the entire uniformly distributed load. It is a simplification that we use because we have all that distributed load that allowed us to solve for the support reactions for the global free body diagram. Here, when I make a section cut, that assumption is no longer true. I no longer have all of the uniformly distributed load acting on the portion of the beam that I'm keeping, right? This portion of the beam to the section cut and to the left only has some slice of that distributed load. And so as a result, all that exists to me, all of the load that I know exists anymore, is only the rectangle from the beginning of the beam down to the section cut itself. What about the height of that distributed load? Is that the same? That's still W. This height is still W. What's the length of the uniformly distributed load now? X1. And so my resultant is no longer here past the section cut. It's just at the centroid of the area that remains. And this resultant is going to be equal to what then? W times X1, because that is all that exists as far as I know. The only thing that I know exists is everything to the left of the section cut. Everything to the right, I replace completely. Wholesale, I replace it with the internal shear force and the internal bending moment. And that replaces everything to the right, including loads, including couple moments, things like that. All right. Likewise, I need to define the distance from, well, on either side. I guess either side would be valuable. Probably this side would actually be even more valuable. What is the distance from that resultant load to the section cut itself.
1 divided by 2.
Yeah, just half the width, and the width that I know about is this variable distance x. So this is x1 divided by 2. That's going to be important for moment equilibrium. All right, what else am I missing? Yeah, the internal resultant. So like we said, when I make this section cut, I'm keeping everything to the left. At least that was our choice. Either side will work. Everything to the right gets replaced with an equivalent internal bending moment and shear force. And so which direction is that shear force going? Well, let me say I don't know yet. But I'm going to assume a direction that it's going. And then if it's wrong, that's fine, because we need to follow a standardized assumption. And so we assume that it's going down. I won't know that until I run the numbers, but this is what we call a sign convention, right? This is a coordinate system. I can flip this around as much as I want. It won't change the answers. It might make the math a little bit harder if I make it like some arbitrary angle from horizontal. This won't change any final answers. If I assume a different direction of the internal shear, it will change my final answer as far as negative and positive. So we have our sign convention for internal shear, for internal bending moment. You need to make sure that you follow those, because that's what I'm assuming you're basing your values off of. So if you get a negative when you should get a positive, you'll lose some points off of that. What about my internal bending moment? Is that going to be clockwise or counterclockwise here? Yeah, here it'll be counterclockwise, exactly right. And so I will call this M1 and I will call this V1 because it's associated with the first section cut. Now let's just review really quick. If I were to have, instead of choosing everything to the left of the section cut, if I made my section cut and I decided to keep everything to the right of it, so here's the rest of my beam, there's loads and everything else going on over here, which direction will my internal shear force be going? Yeah, equal and opposite. This would have been my V1. The moment would also be equal and opposite. That would be my M1 going clockwise. If you make that correct assumption, I mean, if you make the assumption following our sign convention, whether you're using everything to the right of the section cut, or if you're making your free body diagram from everything to the left of the section cut, you'll get the exact same answer for V1 and M1. Just keep that in mind. All right, so I think that's everything that we need except for the obligatory coordinate system, which there's no good reason to deviate from that for this type of a problem. And usually we'll label a point right on the section cut, point O, because usually we like to sum the moments about that point. It makes it a little bit easier to solve for M1, but you don't necessarily have to do it that way. Okay, so before we go through and actually solve for the unknowns here, let's talk about where this section cut is valid. So this is section cut at x1. And I just kind of arbitrarily chose some point between A and B. I made my section cut, and I said this is a free body diagram. But this does not apply to the whole beam. If I made x1 equal to, say, LAB plus LBC, that would be really close to this support right here. Let's just say approximately LAB plus LBC. Maybe a section cut really here close to C. Why is this free body diagram not valid?
It's not in the same domain. It doesn't take into account, well, in this case, mainly that applied moment.
Yeah, that couple moment. So let's just make a section cut just right here. If I was getting close to C, somewhere between B and C, and if I decided to choose everything to the left of my section cut for my free body diagram, I would see the end of this distributed load, which I don't have here. This is never ending. As x increases, so does the width of this distributed load. So if x1 equaled LAB plus LBC, I'd get a distributed load that's all the way applied all the way to C, which is not the case. Also, I'd have this couple moment show up in my free body diagram. I definitely don't have that here. The couple moment doesn't show up at all. And so that's why this free body diagram for section cut x1 has a limited domain. And so how would you define what that domain is? So x1 and I'll just use less thans. It doesn't, again, I don't really, it's academic as far as I'm concerned whether or not these are less than or equal to or just less than. Either way, what is the beginning of my x1 domain? Yeah, it's point A, and because I'm telling you that x1 is the distance from point A, if I'm at point A, the distance from point A is just 0. And so that's the beginning of my domain of x1. Where does this free body diagram cease to be applicable anymore? Yeah, basically right at B. And let's define B in terms of x1. At B, x1 equals LAB. The distance from A to point B is length AB, LAB. So whatever function I define based off of x1 is only valid if I'm plugging in a value of 0 all the way up to LAB. That's the only values of x that these functions are going to be valid for. So this is how I kind of decide how many section cuts I have to make, is that this point here at B, where this domain ends, the reason it has to end is multiple reasons. Number one, my distributed load ends at B. So one rule would be wherever a distributed load begins or ends is what we call a discontinuity, and that's where the domain of one of your functions has to begin or end. Likewise, I have another discretely applied load here. This couple moment is applied at B. That's also a discontinuity. And so the general rule is that you have to make section cuts in between adjacent discontinuities all the way across your beam. So discontinuities would be the beginning or the end of a load, distributed load. It could be where a load, a point load, or a couple moment is applied, which is also this moment right here. It would also apply here for P1. The same thing applies for reactions. Wherever I have a reaction, I need to have a discontinuity as well too. This is just like a force being applied to the beam. It has the same kind of effect as any other kind of force applied to the beam. So these would be discontinuities as well too. And then finally, just the beginning and the end of the beam, even if there's not a load applied to it, that would still count as a discontinuity. So here, point A is a discontinuity because it's the beginning of the beam, a reaction load is applied, and a distributed load begins. Point B is a discontinuity because a couple moment is applied there, the distributed load W ends there, and that's the only two reasons, but it's still one is enough to make it a discontinuity. Point C is a discontinuity because this reaction force is applied there. And finally, point D is a discontinuity because a point force is applied there and it's the end of the beam. So I've got 4 locations of discontinuities, and I need a section cut in between every adjacent discontinuity, which means x1 is going to be a valid section cut between A and B discontinuities. I'll need another section cut here between B and C, and so I will define this distance as x2. Now keep in mind, all of these x's I'm drawing are still originating at A. And so we'll talk about the domain of x2 in just a second. And then I'll also need a section cut here between C and D, and I'll call this distance x sub 3. So that's the rule for how many section cuts you need to make and kind of where you need to make them. But I will tell you specifically in a problem where x is measured from. And I think you can rely on most of the problems we've done so far. It's being measured from the left edge of the beam. But you did have on a homework problem where it was being measured from the right-hand side of the beam as like an alternative. But traditionally speaking, this is the more straightforward way to go about it. Now, let's think about this and let's write down the domains for the other two section cuts as well too. So if I was defining point B in terms of like values of x, at point B, x1 equals what? LAB. At point B, x2 equals what? LAB. It's the same distance from A, and that's our datum for x1, x2, or x3. Now, it's a little bit trickier if I were to say, point B is the same thing as x3 is equal to what? And I think you would be correct if you said either LAB or not applicable, right? Because our section cut x3, its domain is really just from C to D, but technically speaking, point B you could define in terms of x3, but we would never do that because our functions based off of x3 will never be at point B. So let's just write down our domains really quick. So this is our x1 section cut, and we'll wrap up with that in just a second. Our x2 section cut, what is the domain going to be for x2? Well, it's going from B to C, and you already told me that at point B, x2 equals LAB. And I'm going to erase this other bracket over here on the right because I need a little bit more room, because what is x2 equal to at point C? Yeah, it's these two lengths, LAB plus LBC. It's the entire distance from point A, where all these x's equal 0, to this point C. So that's going to be LAB plus LBC. And so I did see on a fair amount of the homework, the natural inclination for some people is to say, well, x2 starts from B and goes forward. So they said x2 is 0 at point B and goes to point C. So they were saying the domain of x2 was 0 to LBC. That is not how I'm going to ask you to do it on the exam. And the reason is when you get to EAS 212 and you're trying to compare maybe the deflection or the slope of a function at like a point B, you want to be able to plug in the same value of x for both of your equations, whether it's the equation that applies from A to B or B to C. It just makes the bookkeeping a lot clearer. Now, it is just a bookkeeping thing, but you still need to be clear. You still need to understand where I'm telling you x is measured from, and that's why it's important. But I'm not going to try to trick you on the exam and throw in a curveball and say, oh, well, now we're going to define x2 as starting at B going forward. I'm not going to do that. It'll always be consistent. EAS 212, maybe Patrick will decide to throw you a curveball, but this is confusing enough without doing that right now. So finally, let's talk about our third section cut, x3. It's between point C and point D. So you can definitely assume that the beginning of your domain is going to be the ending of your previous function's domain. And so we're going to start out at LAB plus LBC for x3. And then it's going to go all the way to point D. And the length from point A to point D, which is how we define x, is LAB plus LBC plus LCD. So LAB plus LBC plus LCD. Easy to make a mistake on that, so I just want to make it as clear as possible. Now, these domains apply just the same exact way, even if I decide to keep everything to the right of the section cut. These domains are not affected by that decision whether or not to keep everything to the left of the section cut or keep everything to the right. It's still completely valid. All right, so any questions about that before we jump into the equilibrium for section cut x1? Okay, so with section cut x1, we've gone through the trouble of making a nice, complete free body diagram for that section cut. And now I need to actually solve for what V1 and for what M1 are equal to. Now, these can both be functions of x, potentially. They could potentially be 0. They could potentially be some other constant value. And so that's where just relying on your equilibrium equation to figure that out is important. We will look at the diagrams in a little bit, and that will be able to tell you, at least quickly, whether or not it should be a function of x, whether it's a function of x to the first power, x to the second power. We can kind of glean that from the loading diagram itself, but you're going to need to give me the function anyway. And so I would recommend doing the equilibrium first, and then when you plot out your diagrams for V and M, that's a way to kind of double check your work and say, well, I don't think it should be linear in this region, and let's go back and double check my work. But either way, you need to do both. You'll be graphing it and checking your work, but also doing equilibrium. And so that's the second step here. Once I have a complete free body diagram at a variable location for my section cut, I'm going to run my equilibrium equations for this specific free body diagram. And so there's only two that we need to run because we only worry about V and M. We don't care about the normal force here, but maybe in EAS 212 you might start doing the same kind of methodology, but also including a normal force as a function, which is a possibility. How would I solve for V1 in this case? Yeah, sum the forces vertically. Sum the forces in that y direction, because all that I care about here is a force in the y direction. And so because there's no other unknowns in the y direction in terms of forces, that's the easiest way to solve for it. So here I'm going to sum the forces in the y direction equal to 0. Let's just go from left to right across this free body diagram. So we start out with AY. AY is going up. My coordinate system says that up is positive. So I get AY. What do I get next? Yeah, minus this resultant. And we would plug in the actual formula for the resultant that we calculated. That's why I recommend putting this actual formula for the resultant on your free body diagram. I think it's a better way to go about it, so you don't have to figure it out at this step. But you could if you wanted to. Either way, it's minus W times X1. And whether you first write down minus R and then maybe slash it out and put W times X1, completely up to you, but I prefer to figure it out on the free body diagram first. Whichever way you want to go about it is fine by me. And then what else shows up in my equilibrium equation? Yeah, and V1 is going down based off our assumption, based off our sign convention, and so it'll be minus V1. So V1 is the only unknown. It's what I'm trying to solve for in this case. And so basic algebra, I'm just going to move that to the left side of this equation, and I'm going to get V1 equals AY minus W times X1. Yeah, Pat?
This is where you tripped up in assuming that AY in the support reaction is going to be the same as what we found from the global diagram.
Oh, sure. Yeah, great question.
Why that is.
Yeah, and so this does not vary with the section cut. And maybe, I guess I don't really have a good way of explaining why it doesn't vary with the section cut, other than saying this section cut is not physically changing anything in the system at all. We're not actually cutting through that beam and like releasing anything and like making the beam fail or anything like that. This section cut is just an analytical way of trying to figure out what's being transferred from one kind of section to the next. It's actually not changing the nature at all of this loading. I can make as many section cuts as I want, and it's not getting rid of any loads whatsoever, right? Another way to think about it is that here, when I look at my free body diagram, it looks like I've gotten rid of a bunch of loads because all that I have left is just this distributed load, just some portion of it. But I look back at my global and I'm like, well, I've got more of that distributed load left. I've got a couple moment. I've got this point force, and I've got the support reaction. So why is it that when I make this section cut and all that I see left is this little bit of this external load, why is this still valid? Where did all these other loads go? Is their effect still seen? This shear and this moment is the resultant loading of P1, CY, MB, and whatever is left of that distributed load. Remember way back in like maybe week 3, we could take a bunch of forces and moments and then resolve them down to one force and one moment acting at a point. That's what V1 and M1 are. V1 and M1 are exactly equivalent to CY, P1, MB, and whatever portion of that distributed load is remaining. That's what we're trying to figure out. And that makes sense because that's the only way this is going to stay in equilibrium if AY is the same. So that section cut is not getting rid of any load whatsoever. All that we're trying to find out is what is the equivalent internal loading that causes the same exact effects of everything to the right of the section cut. Does that help? Okay. So once you've got AY figured out, once you have a support reaction figured out, it's locked in for all of your section cuts. Now, what isn't locked in would be like what we saw here with the distributed load. I mean, that distributed load intensity is not changing. The reason that maybe our internal shear or moment is changing is because when we make the section cut right here, I'm not looking at that entire distributed load anymore. The same thing could happen with a support reaction. If a support reaction was distributed over, say, a couple of feet, maybe like a spread footing or something like that, if I was looking at like cutting up a spread footing, I mean, but here with our support reactions, they're always just at a discrete point. And so if you're just to the left of that point or just to the right of that point, you either get all of it or none of that support reaction in your free body diagram. So that's a nice thing about supports is that we idealize them as being at a single point. And so it's either all of the support reaction or none of it. But either way, the value won't change. OK, so at this point, what can you tell me about the nature of this function V1? How is that going to show up on a shear and moment diagram? Yeah, it's linearly variable because I'm multiplying by x to the first power. All right, and I could have figured that out. And this might even be as good a point as any to kind of double check our work. How do I know that between point A and B, the shear should be linear? What's the touchstone looking at the loading diagram that tells me that's going to be the case? I've got a distributed load. That's part of it. What specifically about that distributed load tells me that the shear is going to be linear? Yeah, it's a constant value. W is constant. And the slope of the shear diagram is the value of W. Because W is constant, the slope is constant, and that's why it's going to be linear. Exactly right. We can even go one step further, and I can say W is pointed downwards as a negative constant value, so I'll have a constant negative slope for V. Exactly right. So you can kind of do that checking as you go through. The next thing that we would solve for would be the internal bending moment, M1. And you can sum the moments at this point. Once we have V1, I can sum the moments about here, that door, right, I-405, wherever you want, and you're still going to get the same value. But the easiest place to sum the moments about is usually going to be right on the section cut itself. And there are some benefits to that. We don't need to know what V1 is before we solve for the moment if we sum the moments about 0.0. But so that's the most common place to sum the moments about. Summing the moments about the section cut, we often call it 0.0. And so at this point, it's really all the same actors for this free body diagram causing a moment about that section cut. AY, this resultant, but V1 won't, but M1 will. If I had a couple moment on this free body diagram, like if I would have chosen everything to the right of that section cut, then I would have had this couple moment to deal with as well. I just would have thrown it into the moment equilibrium equation just like everything else. But here, because my section cut keeps everything to the left, I don't have to deal with that couple moment over at point B. Right? Is the effect of that couple moment at point B still being felt by this free body diagram? Absolutely. Part of its effect is in AY. Part of its effect is in this couple moment over here as well too. All right, so AY causes a clockwise moment about O, so it'll be a negative. And what is its moment arm?
X.
Just X1. What about my resultant R? That's causing a counterclockwise rotation about O, so it'll be a plus, and that's W times, X1. And what is its moment arm? Yeah, it's from here to here. We said that's X1 divided by 2. And what else causes a moment about O? Just the internal bending moment, M1. And that's counterclockwise on this free body diagram, so it'll be minus M1. So all I need to do is rearrange this equation right here to solve for M1 by itself. And I get that M1 equals Wx1 squared divided by 2 plus I'm sorry, this would be a negative. Yeah, I'm sorry. And yeah, because this should be a positive, right? This should be a negative Wx1 squared divided by 2 plus Ay times x1. Let me move this over here, plus m1. Now, there's a couple checks that we can do here. So the highest order variable in this equation is squared. And as such, this is going to be a parabolic shape. And that comports with what I know about the shape of the shear diagram. I know the shear diagram is going to be linear. And so based off that calculus kind of relationship, the rate of change relationship between shear and moment needs to be parabolic. So that checks out. Another way that I can check my work here is not just the shape of the actual equation, but the equation itself. I can't go from shear, well, I can, but I can't do it easily, and I'm counseling against it. I should not just integrate shear to get my moment equation. Does it work out here? Is this the antiderivative of this? It is. The reason that I don't want you to do it is because it works out here, but it's not always going to work out. For example, if I had a couple moment apply to A, that's going to show up in this M1 equation as an extra constant out here. If I integrate this, I technically get a constant of integration, but everybody forgets about that. And then solving for it's kind of a pain. And so you need to do the equilibrium equation to show me the moment equation. You need to show me that work. But you should check your work and just say, is this the derivative of this? And if it is, then you're good to go as well too. It's really just the constant of integration that could throw you off. And definitely speaking, for the section cut x2 or the section cut x3, you will get a constant of integration that's not 0. The reason that a lot of students kind of fall for this is that for the very first section cut, it usually works out pretty well, which is great. But then they get to the other section cuts and they forget about the constant of integration and they lose it and then they lose some points, and so I don't want you to do that. So show me the equilibrium equation, solve for the moment that way. Don't get lured into antiderivative functions because it's going to lead you potentially to a mistake. All right, so we've got these functions right here for V1 and M1 that applies on the X1 domain from 0 to LAB. And so if I wanted to, I could start drawing my diagram for shear and for moment right now if I wanted to. And on the exam, I'll provide you with the given figure, and then I'll give you the axes down below for shear and for moment. And that's the best way to kind of line everything up. But these functions that we just calculated, V1 and M1, only apply to this first domain right here. And then, so usually what you would do is you'd plug in the beginning value of x, which is 0, the ending value of x, which is LAB, get the values and plot them on your diagram here. Now, there's a graphical way to kind of check our work as well too, but you will need to plot out the results. And I might also ask you for a maximum or a minimum value, which we've talked about a little bit in class too. Here, we're going to get a diagram that jumps up some value, AY. So we start at 0, we jump up because we have a point load, and then I get a uniformly distributed load going down. And let's see, it's hard to say where it's going to end up, so I'm just going to draw it like that. It's not necessarily going to be symmetric like this. It's just a general kind of figure, but it's going to be linear going down. And then we'll talk about what happens next. Same thing with moment. We're going to start out with moment of 0. It's not going to jump up or down because there's no couple moment applied there. So it starts out at 0. It's going to have some positive slope starting out. And as I've drawn it right here, this point where the shear equals 0 should be a flat spot on the diagram. And then here at the end, there should be some downwards slope. Now, as I've shown right here, this is not accurate because we don't have values on this yet. I don't know what the actual location or point of 0 shear is going to be. I'm just showing you the calculus-based relationship where if I'm asking you for a maximum of the moment, you would just find where the shear is equal to 0. It's easy to find with a linear function. Plugging that value of x to your moment function, that's where you would get a max. Let's see. I don't know what else you want to go to in more detail. But how about this? Any questions about the free body diagrams for section cut x2 or x3? Yeah, Pat.
Yeah, so when the shear passes that 0 point, how does that equate to the distributed load?
Oh, sure. So another way to think about that is you could, well, I mean, the change, the change in shear has to be equal to AY to get down to this point 0. So, I mean, basically, the slope of this diagram right here is equal to the distributed load. So if I was looking at the slope of this, the slope of this diagram here, for every 1 that I go over, I go down W. So the distributed load here is the slope of the shear diagram. And that's why when I get to section BC, what's the slope of my shear diagram going to be? How much distributed load do I have between B and C? 0, so it's going to be flat. And so that's the relationship between the distributed load and the shear diagram, is that the slope of the shear diagram at any given point is equal to the value of the distributed load at the same point. Now, that's not the only thing that affects the shear diagram, but it will tell us the slope at any given point. Shear diagrams can jump up or down as well too, and that's due to a point force. So distributed load tells us a slope. Point forces tell us a discontinuity jumping up or jumping down. That's why here at point A, it jumps up this value AY because I have this point load, this reaction AY going up. So that's the relationship between loading diagram and shear diagram. Jump up or jump down based off of a point force. So it'll happen here, it'll happen at CY, it'll happen at this P1. There'll be a discontinuity, a jump up or a jump down at each of those points. And then for distributed loads, that's just telling us the slope of the shear diagram at any given point. So here between A and B, I've got some constant negative slope. What is the slope of my shear diagram for the rest of the beam? 0. Now, does that mean it's just going to be flat all the way across? No, it's going to jump up and down, but between those points of discontinuities, it's going to be completely flat. Exactly right. So what's going to happen here is it's going to look like, so between B and C, it's going to be flat. Once I get to point C, it's going to jump up some amount. And I know in this case, it's going to have to go above the horizontal axis, only because I know at some point it has to go back down with P1 down to 0. So then it'll go across like this and then jump down. So my shear diagram is going to look something like this, but again, it all depends on the actual values of the variables given. So again, one more time, start out at 0 for either diagram at the far left end. As I go from left to right, any force pointed upwards will make my diagram jump up the amount of that force. So here I start out at 0, I jump up to AY. And then between A and B, I have a constant negative distributed load, which means I have a constant negative slope in my shear diagram. Once I get to point B, that couple moment does nothing to my shear diagram. And so there's no jump up or down at B. Between B and C, there is no distributed load, no point load, so nothing can happen to shear in between B and C. But as soon as I get to point C, I've got a reaction CY. CY is pointed up, and so my diagram is going to jump up. And how much is it going to jump up? A value of CY. So from down here up to this point, it jumps up that value CY. Between C and D, there's no point loads, no distributed loads, so there's no slope between C and D. Once I get to point D, I have to jump down, and I'll jump down the value of that point load P1. Yeah?
What does the couple moment do to the moment diagram?
Great question. So we were talking about point forces are making the shear diagram jump up and down. For the moment diagram, the question is, what do the couple moments do to the moment diagram? So what's the answer?
It's actually brings it down because we have a negative.
Well, this is tricky as well too. So we know that this couple moment is going to do something. And so then the question is it going to make it jump up or down? And we talked about this a couple times in class as well too. This couple moment is going clockwise, and so a lot of people just think right away, well, clockwise is like negative as we usually think about it, so it's going to make it go down. That's not the case. Any clockwise couple moment as you go from left to right across a beam is going to make your internal bending moment jump up. And we can prove that pretty quickly. The diagram in the Hibbler textbook, the recommended text, has a nice little diagram that kind of proves that. So let's go ahead and take just a section of a beam with some differential length dx. And right here at that point in the beam, we have a clockwise couple moment. I'm just going to call it m naught applied to the beam. Now I've made a section cut here and I've made a section cut here, so I've got to replace everything on either side with an internal moment and an internal shear. And so here I'm going to draw both of those in the assumed positive direction. So on the left-hand side, that'll be V and M. On the right-hand side, it's going to be V and it's going to be M. But here, I know that M on the left and M on the right aren't going to be the same. I know there's going to be some change in moment, and so to capture that, I'm actually going to say the moment over here is equal to the original moment plus some change in moment I'll just call delta M. The reason I'm drawing that, I'm trying to capture what is the change in moment from here to here. And the change is simply the original value plus some differential moment, some change in moment. And so if I were to sum the moments about this point, we'll just call it O. If I sum the moments about point O equal to 0, I get this M going clockwise, so negative M. I get this moment here going clockwise, so that's negative M naught. And then here I get, oops, I'm sorry, I drew this the wrong way. This should be assumed positive that way. Sorry about that. This is going to be going counterclockwise, so that'll be plus M plus whatever that change in moment is. And so I can cancel some stuff out. I get this negative M cancels out with that positive M, and I get that the change in moment dm equals m naught. And because I'm assuming the positive sense of the internal moments here, it's telling me that the change in moment is positive this couple moment as I go from left to right across. So remember, counterclockwise here, we're not showing any kind of internal moment, and this doesn't make any difference for anything anyway. So just keep in mind a positive couple moment will cause, or sorry, a clockwise couple moment will cause a positive jump up in our moment. So using that information, so here, let me redraw this just a little bit. Here with my moment, I'm going to draw it like this, where this is still the maximum, where the shear equals 0. And then what is going to happen at point B? It's going to jump up whatever that value of MB is. That's because the couple moment, the clockwise couple moment MB, will make this jump up. What happens to my moment diagram between point C and point B and point C? Yeah, I have a constant negative shear, so I have a constant negative slope here. And so I get a constant negative slope. I'm just going to assume the final value here. I think this is okay, because how do I know it's going to have to be below the horizontal axis here? What happens between C and D? I get a constant positive slope, because my shear is a constant positive value. So this has to have a constant positive slope in my moment diagram. And I know that we have to end up at 0 at the end. It's relatively more complex, but that's how I know that the shape at least went below the horizontal axis. And then my moment diagram, again, the beginning and ending values of each of these sections are not clear without discrete values for the functions, but it's going to look something like that. Parabolic, jump up, constant linear down, constant linear slope up. That's the general shape of what it's going to look like. All right, just for time's sake, I want to make sure that we spend some time on the geometric properties as well too. So unless there's a quick question about anything lingering about this, let's go ahead and jump to geometric properties. Yeah, question.
Real quick question.
Yeah,
So
of course.
On the test, on these diagrams, like the graph of shear moment,
Right.
how much information do you want us to actually put on the diagram?
So I'll try to be as clear as possible. It's going to be the beginning and ending of any section. So you need to give me the value at the beginning and the end of section AB, BC, CD. So I need values at the beginning and the end of any section cut, like free body diagram that you've made, and then like a maximum value. So I'll say critical points, and in parentheses, I say beginning and end of any sections, and then maximum or minimum values. That's all that you're going to need to put down. You'll need to label your axes, right? So V and M, I'm not going to label those for you. And what else would you need to provide? Whether it's in the values here or on your axis, I want to see units as well too. And I say that on the exam, I say label and provide units. And so the easiest place to provide units would be right here. So every time that you're labeling a value here, you don't have to put kips, kips, kips. Just put kips right here and it takes care of it. I already provide on the exam, I provide like light gray lines that go down all the way here. So you should be able to line everything up pretty easily. Okay, so let's talk geometric properties, and let's make a larger, more complete kind of table along the lines of what I've been proposing in class or trying to get you to use in class. And again, I understand that space is at a premium when we're dealing with these tables and these diagrams. So I'm going to try to use as much space as possible to make it as clear as possible. What I have seen some students do is rely on maybe two different diagrams. One of them they use for centroids and one of them they use for moments of inertia. Or I've seen some students split it up where they have one figure for all of their like y bar value for centroid and then ix like moment of inertia calcs. All the calcs that rely on the y values. Then they have another figure that deals with all the x values, which you use for calculating x bar and iy. So if you want to try to split it up that way and deal with each axis separately, that might be a way to keep your diagrams as kind of clean as possible. So I think that's maybe a good way for us to try to split it up right now as well too. So what kind of shape do you want to deal with? Do we want to deal with this is a table methodology, so we want to deal with something with elementary shapes. So rectangles, triangles, circles. Does anybody have any preference on what kind of a shape we're talking about? Do we want negative shapes on it? Do we want to deal with that?
The one that we had on the homework, that was like a little bit complicated.
Yeah, trapezoid with a circular hole in it, right? Yeah, so let's go ahead and do that. Let me refresh my memory. Okay, so it's this one right here, correct?
Yeah.
Okay, great. And so here we'll have some actual values to deal with as well too. So let's and it's got a circle, a void right there. All right, so how many shapes do you see if we were going to break this down into elementary shapes? Yeah, I think 3. And technically speaking, you could get away with 2 because the back of the Hibbler textbook and that table that I posted up on OneNote has the geometric properties for a trapezoid as well too. I don't know if I'd recommend it, because those trapezoid equations get to be a little bit hairy. You get a lot of variables, and so it's just a matter of the more elementary you break up the shapes, the easier each individual term is going to be. And so I prefer dealing with this in terms of 3 different shapes, and I think that a lot of you would do the same. So I'm just going to draw a vertical line here to break this up into those 3 different shapes. And let's just deal right now with the values that depend on like y distances. So here, if this is my x-axis right here, and this is my y, let's just focus on calculating y bar and ix. And so we want to calculate y bar and ix. And I'm actually going to calculate ix sub c, which is a moment of inertia about an x-axis, an axis parallel to the x that goes right through the centroid of the overall shape. So what is y bar? Just in words, what is y bar?
Y component of the centroid.
Yeah, it's the distance from the x-axis to the y coordinate of the centroid of the overall shape, right? It's for the overall shape. So that's going to be somewhere roughly here, approximately. And so I'm going to say this is my overall centroid, and it has a y coordinate of y bar. And so what is the function for y bar? I'll tell you it's a ratio.
Sum of x, or sorry, y tilde times the area over the sum of the total area.
Exactly right. So Pat's saying it's the sum of y tilde times the area of each element divided by the sum of the area of each element. So the numerator is what we call the first moment of area. It's just the area times some distance divided by the area. So this is like a weighted average is really all that's going on here. And when I say sub I, I'm just talking about I being like an indicator for each of these individual shapes. So I want to demarcate each of these as a shape. So this rectangle I'm going to call shape number 1. This void, this circle, I'm going to call shape number 2. And this triangle I'm going to call shape number 3. So I here is just a 1, 2, 3 subscript is all that we're dealing with. And so for each of those shapes, I need to know y tilde. And what is y tilde?
Distance of the centroid over each shape.
Yeah, it's the distance from the x-axis, or whatever datum we choose, to the centroid of each shape. So I need to show the centroid of each shape on this diagram. So here, the nice thing is that this circle and this rectangle share a centroid. So because the void in this circle is located at half the height of the rectangle, they both share the same centroid, which makes life a little bit easier. So I'm going to show a smaller centroid here, and this centroid is for both shape 1 and shape 2. And again, all that we're drawing right now is the y components. We could draw a separate diagram if we want to calculate x bar. It's the same exact procedure. So here, I'm going to call this distance y tilde 1, comma y tilde 2. And in this example, what's it equal to? Just 150. All right, what about this triangle here? It's a triangle, and so the centroid, we can get this distance from the table. And again, you're responsible for rectangles, circles, and triangles for your note sheet. This is y tilde 3. And what's the formula for this y tilde 3 value?
1/3 times.
Yeah, 1/3 the height. And it's 1/3 the distance from like the heavy end of the triangle. Because if I inverted this triangle, this centroid is not 1/3 of the height from the skinny end. It's 1/3 from the heavy end of the triangle. Just keep that in mind. It's an easy mistake to make. And so here, y tilde 3 is going to be equal to what? Yeah, the overall height here is 300 millimeters, so this will be just 100 millimeters. And then based off all the other geometry, we can calculate the areas and everything else as well. But at this point, I think it's really important to start organizing this into a table, which was basically what the request was for kind of this subpart. So let me start a table, at least for this y bar calculation. So all right, so I need to keep track of all these properties for each individual element. And so the first thing that we're going to keep track of is just which element are we talking about. Number 1 is the rectangle. Number 2 is the negative circle. Number 3 is the triangle. And so I need to tabulate y tilde, and a sub I for each of these. And so you might go to the trouble of writing down like what the dimensions are if you want to keep it in your table. So I could just say relevant dimensions like b and h or diameter or something like that. But I'm just going to go straight first to calculating the area of each. And so here, this will be millimeters squared. And so the area of a rectangle is going to be the base times the height. Here, it's 200 wide and 300 tall, right? And actually, I've got the whole table here as well, too. We can just plug in the values for the triangles and the circles as well. Here we go. So we've got 6 times 10 to the 4th. I don't need to put units here because it's already in millimeters squared. For the rectangle, we've got 2.25 times 10 to the 4th. For the circle, it's just a pi r squared. And then the last area, A3 for the triangle. Oh, I'm sorry, it's the other way around. This is actually for the triangle. I'm using a different indicator for the circle and the square here. And the triangle, I'm sorry, it's negative 1.767 times 10 to the 4th is the area of the circular void, and the triangle is 2.25 times 10 to the 4th millimeters to the 4th, millimeters squared. So the key here is that the area of this void is negative. And that's important because if you don't account for that, it's like you're adding the circle on top of the shape instead of subtracting it out. So you need to keep track of this as a negative value. Next, I need to write down all of my y tilde values, and this will be in millimeters. We've already calculated those over there. For the rectangle and for the circle, both of these are 150 millimeters. And then for the triangle, we said it's 100. Now, this distance is not negative for the circle. This y tilde 2 value is not negative for the circle. Only the area is negative. The distance is simply the coordinate as we have the given coordinate system. It's not going to be a negative value. It would be negative if it was down here below the axis. But here, it's a negative area that has a positive y coordinate. There's nothing wrong with that. And then finally, the only other thing that I need here is to multiply y tilde times the area for each of these shapes. And so all that I'm doing is I'm taking the value in this cell, multiplying it times the value in this cell, and then getting a value of the two of them multiplied together in each of these cells. So if I were to sum up all of the left column cells here, if I were to sum all of these up, that is the denominator of this formula. And so I can take this and I can plug it into that denominator of that formula. If I were to sum up all of these y tilde times a terms, that is the numerator of this function. And so really it's just taking the sum of this column, dividing the sum of that column, and that will give me the y bar value, whatever that ends up being. And you could do a little bit of checking here. I mean, what is the upper bound? What is the highest value you should expect to see for y bar for this shape? 150 is the highest it could possibly be. What's the lowest it could possibly be? Yeah, 100. I mean, that's pretty coarse, but if you made a small mistake with like a area or a distance or something like that, you might get like 165, which just can't work, right? So that's a good way to do a quick kind of reasonableness check on your calcs. Depending on the relative size of each of these shapes, I mean, if we had a shape that looked, like this, where the triangular portion is nearly nothing, you could expect the centroid to be closer to the centroid of the rectangle and the circle. If it was the other way around, if I had a super, super narrow rectangle and a huge triangle, you know, something like this, my centroid should be close to that of the triangle. So just reasonableness type checks like that I think are valuable. Again, on the test, if for some reason you get bogged down on time or you need to move on and you know something's wrong, just explain to me why you know it's wrong and I'll give you some extra points for that, which is a lot better than just saying, well, I know something's wrong, I don't know what it is exactly, but I could maybe explain why, but not writing it down, you wouldn't get any points for that. But just keep in mind, it's always a narrative you can write down and kind of explain to me what you're thinking. Okay, so that's all that we need to calculate the location of the centroid, that y bar value, but we can continue on this table and that diagram to also calculate the moment of inertia. And so first I want to just look at the moment of inertia about the given x-axis, which is the base of this shape. Now the moment of inertia can be taken about any axis that you want. You just need to be careful and read about exactly which axis I'm asking for the moment of inertia about. So if I'm taking the moment of inertia about the x-axis or any other parallel axis, the function, the actual formula is still the same. It's equal to I x naught plus a times dy squared. That looks like d times y squared. It's d sub y squared for each individual shape. And I sum up all of each individual shape's I x naught and their a times dy squared values. I x naught is what? It's the moment of inertia about what axis? The centroid of each individual little element. And where do I get these values for I x naught? In that table that you need to put into your notes. So this I x naught depends on the shape, and it's the moment of inertia of each individual element, whether it's a rectangle, circle, or triangle, about its own centroid. Yeah, Pat?
Side question about the notation.
Sure.
For that initial, the initial moment of inertia, they have x or I bar, x prime. Like, is it really a standard?
You'll see, no, there's no standard whatsoever. So if I look at my steel book versus my concrete book versus my timber book, it's completely different notation in every single one. So what's most important is that you look at the diagram and figure out which axis I'm asking for the moment of inertia about. And so if I say about the x-axis and I give you a figure like this, it shows the x-axis right here, you know it's a moment of inertia, not about the centroid of the shape. If here I had labeled this like x sub c, and I said give me the moment of inertia about the x sub c axis, you just need to verify it off of the diagram. If I said give me the moment of inertia about an axis parallel to the x passing through the centroid, that is this axis, and I may or may not label it, but you just need to be clear either from the instructions and or the figure which axis I'm asking for the moment of inertia about. But there's no convention about whether that's x, x prime, x naught, x whatever. It's kind of frustrating, but it just means that you need to rely on the figures in the explanation. But I wish there was a standard, but there's really not, unfortunately. So, like I said, this formula doesn't change whether we're taking the moment of inertia about the x or the x sub c, as I'd call it here. The only thing that really changes is dy. Yeah,
Just to clarify,
of course.
the area is for the local shape, right? Not the overall.
Exactly right. This area right here is the area of the individual element. Exactly right. Just likewise, d sub y is the perpendicular distance from the centroid of the individual element to your axis of interest. And so let's do these kind of one at a time. So here, I x naught, it's going to be a different value depending on whether it's a rectangle, a circle, or a triangle. And you would look to the table to figure that out. And so if I go to the lectures here, and I go to the excerpt from the appendix has the moments of inertia about the local centroid for a rectangle, for a triangle, and for a circle. These three squares are really what you're responsible for putting, in your notes. And so here, I'm going to start like a whole new set of columns, and one of the things that I want to tabulate is those I, X, naught values. For the rectangle, it will be 1/12 base height cubed. For the circle, it's going to be pi times the radius to the 4th divided by 4, right? Is that right? 4 or 2? I always forget this one. 4. Yeah, 1. Yeah, because when we add them together, this is pi over 2 for the polar moment of inertia. So that's exactly right. What's wrong with this equation, other than me forgetting it off the top of my head? It's got to be negative, exactly right. This has got to be a negative value because it wouldn't make sense if this whole added to the moment of inertia of the shape. It's got to take away from it. So this is going to be a negative value because it's a void. And then down here for the triangle, it's going to be 1 divided by 36 base height cubed. Now the base and the height for the rectangular formula is not the same as the base and the height for the triangular formula necessarily, right? This is the individual width of the rectangle and the height of the rectangle. This is the width of the triangle and the height of the triangle. It just so happens in this example from the homework, I believe that they end up being pretty similar to each other. No, the height's the same, the width is going to be different. So just keep in mind, this B and this H is individual to the shape. Yeah, Pat?
I have a question about the triangle moment of inertia, why there's not a Y. Like, that's really...
Yeah, I don't know why they don't put it there. I mean, it's just the same exact formula. They do it for the rectangle as well, too. So just keep in mind the figure that they have shown. There's nothing wrong with having you just rotate that. So they give you the centroid is here, and they say this is your x or x prime axis or whatever they say. I'll just call it x naught here. And they say I x naught equals 1/36 base height cubed. So if I cared about this vertical axis instead, we'll call it the y naught axis. All that you really need to do is just kind of rotate your conception of this triangle, and it's going to be 1/36 height times base cubed. That's really all that we're talking about. It's just rotating it. They're just saying that the formula that applies to this axis can be applied. I mean, you could think of this as the base now, and this is the height, and just kind of rotate your conception. I don't know why they don't tabulate them both, but all you're doing is just rotating it.
What's interesting to me is that they do explicitly
For the
show
rectangle.
the rectangles.
On the circle.
Yeah. Yeah, for the circle, it's even funnier, right? It's even funnier for the circle. So there's no trick going on. They're just lazy. But I actually see that a lot in like my SEAL manual. They do the same thing. They only show it for one direction, but they show it both for the rectangle. They even show a square, which is, again, annoying. But anyway, all of your, so this is like the lowest possible moment of inertia of a shape. Because as soon as we start looking at some distant axis that's parallel to this, we start adding in this parallel axis theorem term. And this is always going to increase your moment of inertia, at least the magnitude of it. Obviously, if we have a negative moment of inertia already, this is going to increase the magnitude of how negative that moment of inertia is. So what we need to do for that is we need to tabulate the area of each individual element. Well, fortunately, I already did that. It's already in my table, which is great. So what we really need to focus on is dy. And so I need to tabulate dy for each shape. That's just a distance, and so it's going to be in millimeters as well, too. Ix naught is going to be in millimeters to the 4th. Dy is going to be in millimeters. And what is the definition, remind me, of dy?
From the center of the axis of interest.
Yeah, it's the perpendicular distance from the centroid of the element that we're interested in to the axis that we're taking the moments of inertia about. So I've got 3 different elements here with 3 different centroids. I guess these centroids are the same. It is the perpendicular distance between this centroid and our axis of interest. Here, my axis of interest is the x. So that means that this is perpendicular to that axis of interest and the distance to this centroid. So this is dy1. and it's dy2, because this is the centroid of shape 1 and shape 2. Likewise, this is dy3, the perpendicular distance from x to the centroid of the element. And each individual element might have a different location of centroid, so you gotta be careful about that. So once I have this value, I mean, for this case, it's really easy because here dy is just equal to y tilde. For this example, it's not always gonna be that way. And so I would tabulate those values here, and then I just need a new column that's going to give me the area of each shape times this term dy squared. Now, I can't count how many times I've seen the mistake of forgetting to square dy. It's just so easy for one reason or another to forget it. So maybe do yourself a favor, put parentheses or like highlight this, the exponent. It's just so easy, especially when you're in the middle of a test, to remember that. I make that mistake all the time too. It's not just a student thing. So don't forget to square that value when you're tabulating this. And then all that we would do is sum up. Oh, forgot one important thing. Are all of these positive because dy is positive? No, because the area of the circle is negative. So dy squared is positive, but the area of that circle is negative. So this is going to be negative, but both of these will be positive. Just keep that in mind. Same thing as before. That circle can't be adding any moment of inertia. It can only be taking it away because it's a void. So both of these terms have to be 0. And all that I would do is just sum up this column of the I x naughts. I would sum up this column of the a times dy squareds. And then here I'm not dividing anything. All that I'm doing is just summing them up even for one more step. So this is the first term, and then this is the second term. And that's pretty much it. Now, we're out of time, but I want to wrap up with just one thing really quickly. If I was instead taking the moments of inertia about the x sub c axis, the centroidal axis parallel to the x, what changes do I get to the terms in this equation? Just dy. And so what is dy for shapes 1 and 2? So the centroid of the shape is right here, or the centroid of each element is right here to the centroid of the shape itself. So this is our dy1 and dy2 if this is our axis of interest to the centroid. Likewise, this would be dy3 for the third element about this centroidal axis. The only thing that changes is dy, and so having that on a diagram might be helpful. All right, I've got to run out to the west side, unfortunately. I'm going to hook this up to my computer, start recording it. It should be up in a few hours. If you have any other questions, I'll try to answer as much as I can. But it's going to be, the more detailed of a question, the sooner, the better. I can't promise I'll get to all the email questions that I've gotten already, but I'll try to do my best. And otherwise, I'll see you guys early on Monday.